introduce yourself. So I'm handing over to you, Roxana. So please go ahead and introduce yourself and proceed.
Yeah, thank you, Susan. Thank you for the invite. My name is Roxana Istrate, and I'm a third-year PhD student at the IBM Zurich lab. And currently I'm working in a deep learning group that aims to automatize the architecture search for convolutional neural networks. Convolutional neural networks are usually used in image classification tasks, but not only. So today I'll present the content of our latest NIP submission about the TAPAS framework. TAPAS comes from Trainless Accuracy Predictor for Architecture Searches. And this framework, just like the name suggests, aims to speed up the architecture search of convolutional neural networks for a variety of datasets. That's the key point. First, I will shortly detail the motivation behind our work and the current state-of-the-art solutions. Second, I'll present the TAPAS framework's methodology, which is based on three main components: the dataset characterization component, the lifelong database of experiments, and the accuracy predictor. Furthermore, I will present the results of our accuracy predictor compared to other state-of-the-art predictors, and the results of employing our accuracy predictor in architecture search. We conclude with final observations and other improvements we currently have in our pipeline. So, as most of you probably know, the architecture search of a network that meets the final user expectation is an expensive empirical process. We start with an initial network. I hope you can see my pointer because that's important in the
See your pointer, yes.
Okay, perfect. So we start with an initial network, and this network can be a network that we've already worked with and we know it retrieves good results, or state-of-the-art networks, such one of the ResNets or DenseNets. We trained for some time because we actually don't know for how long. It could take hours, days, or weeks. And then we check its accuracy. In the rare cases when we are actually happy with the accuracy, then we just serve this model. In the cases when we are not happy with the accuracy, then we have to start tuning hyperparameters that might include the network architecture itself. This is a never-ending loop that can easily take months for one dataset only. Obviously, this solution does not scale in front of a large number of datasets. So to design a cost-aware automated search, we need to consider a couple of things. First, we should be able to reuse all our knowledge from previous experiments, because if we always restart from scratch and trash the experiments that we did before, then we will always have to pay a large amount of time to do some predictions. Then it would be ideal to predict the accuracy of a network trained on a dataset without actually training. So to predict the accuracy of a network without actually training it, just by looking at the network structure. Third, we should be able to dynamically adapt our predictor for different datasets, regardless of their difficulty. We should employ an architecture search of a large number of different networks configurations in just a few seconds. One of the first state-of-the-art architecture searches was the Google's large-scale evolution approach. The idea was inspired from genetic algorithms and assumes that we start with a small population of poor-performing networks that we constantly mutate and train until we found a good enough performer. Each newly created performer has to be trained, and they train it for roughly 30 epochs, and they put back in the population. Since this experiment involves trainings of tens of thousands of networks, it's extremely expensive. The authors claim to have used 250 workers, which this translates to GPUs, for 10 days to reach 94.6% accuracy on the CIFAR-10 dataset. CIFAR-10 dataset is a relatively small dataset. It contains only 60,000 images, and it has only 10 different classes. Therefore, this approach can easily become impractical for large datasets. Peephole is another framework that makes a step forward, improving the search time by predicting the network accuracy without training it. They encode the network structure and the epoch number. So here we see that for each layer, they do a sort of encoding that goes into a network that gets translated into some embeddings. Then they connect these embeddings with the embedding of the epoch, and they try to predict the accuracy of a network at a specific point in time. Now, since nowhere in their pipeline they say something about the data set, this approach is dataset specific, because we know that an accuracy is practically the performance of a network on a dataset. The same network can have 90% performance, for example, on an easy dataset like NIST, but can have a totally different performance, like 60, 40% on very hard datasets like CIFAR 10, CIFAR 100. Therefore, only looking at the network structure, it's impossible to make accurate predictions across different datasets. When a new dataset comes into our framework, and this yellow box here represents the dataset, the first thing that we do, we pass this dataset through the dataset characterization component that I already mentioned before. And this dataset characterization component computes one number, which is the dataset characterization number. And this number gives us a hint of how easy or how difficult the dataset is. I'm going to detail how this dataset characterization number is computed. But for now, what we should say is that this number is used to filter from our lifelong database of previously done experiments only the experiments that have been executed on similarly difficult datasets. So we do this filtering, and only on the experiments that are similar, that have been executed on datasets in similar difficulty as the one that we just received from the user, we train the accuracy predictor, the trainless accuracy predictor. This accuracy predictor itself is a very small network, 2 LSTMs and dense layer that outputs one single number, which is the accuracy of the network. This should take a couple of minutes in training, but obviously depends on how big is the ground truth. Once this accuracy predictor is trained, then we can make predictions. And it receives as input the dataset characterization number, which we computed, and a completely unseen structure of a network. And it aims to make a prediction of the accuracy of the network on the dataset at hand. Please stop me whenever it's something unclear, because it's gonna become probably even more unclear as I go on. So are there any questions so far?
I don't see any questions in the chat yet, but people can go ahead and ask.
Okay.
Pretty clear so far. Yeah, pretty clear so far. Yeah.
Now, I will shortly explain the data characterization process, although this is a side work and itself would need an entire presentation. This is another paper that we submitted. The main idea is that we try to create a fast algorithm that would rank data sets from easy to hard. We employ 14 used datasets in image classification tasks, and we design 10 small and fast networks which trained on these datasets would give the same ranking of the dataset difficulty as the ResNet 20 would give. These are the networks that we've designed. 7 of them are completely static, so they don't change depending on the dataset, but 3 of them change their structure and scales the topology with the number of classes. For more details, I've already put the paper at the end in references, so you can check more details there. But the goal was that this dataset characterization process would go very fast and look at the network, look at the dataset and give a number between 0 and 1, because this number is actually an accuracy, the accuracy of what we call a probe net, which is a very small network compared to state-of-the-art networks. But that would already give you a hint of how difficult or simple this dataset is. So these probe nets give you an accuracy between 0 and 1. The higher the number, the easier the data set. With this, we pass all our data sets through this characterization phase, and then we rank them. Now, why is this important? Like I said before, after we collect this dataset characterization number, we do a filtering of our lifelong database of experiments to take only datasets that are similar in difficulty. Now, below, we see why is this important. In the left-hand side, we've trained our accuracy predictor on datasets that were not close in difficulty with the dataset that we were targeting. So we've trained the accuracy predictor on these two green datasets, the Street View house number and the German traffic sign roadmap dataset. These two are very easy. They easily go above 90% in accuracy. And then we want to make the AP, the accuracy predictor, make predictions on datasets that are more difficult, like CIFAR 100. And we can see that the predicted accuracy is mostly very optimistic. And the reason for that is that the accuracy predictor in its training was only used to see datasets that were very easy. Therefore, he's biased to predict high numbers. When we change this, and instead of training the accuracy predictor with datasets that are far in difficulty from the targeted one, but we actually train with datasets that are close in difficulty, and we used for this subsamples of ImageNet, then we see that the prediction is very correlated with the accuracy that we obtained through training. Therefore, it's important to tune the ground truth of the accuracy predictor according to the dataset, to the difficulty of the dataset that we are targeting. Now, the TAP is encoding the networks layer by layer based on an encoding vector, which contains relevant information about the current layer, the first half, but also about the subnetwork up to the layer. So information, if we want, for example, to encode layer 3, we encode information about layer 3, but also information about parameters between layer 1 and layer 3. So the current layer information contains the layer type, which is a one-hot encoding, then ratios between the input and output height and depth, the number of weights the new layer brings, while the subnetwork between the input and the layer that we want to predict contains information like the number of layers, the inference floating points operations it's doing, the inference memory, and accuracy. And this is a very sensitive point because we don't actually include the accuracy that we want to predict in the encoding. So to clarify this, we have to check how the accuracy predictor is actually doing the prediction. Below, we see one network with NL layers, and at every step, we do the encoding of 2 consecutive layers. So first, we encode layer 1 and layer 2. We compute all the information that I already discussed about in the encoding, and in the accuracy, in the place of the accuracy for the input layer, we put 1 over the number of classes, which is a reasonable number, because it's like a random choice. If you would have only an input layer, the network wouldn't learn anything. While for the layer that we want to do the prediction for, in the accuracy place, we put 0. We concatenate these 2 vectors. Together with the dataset characterization number, we pass it through the training accuracy predictor, and we get the accuracy of layer 2. There is a mistake in the slide. It's not A1, this should be A2. So it's the accuracy of the layer 2. Now, the accuracy of this layer goes in the encoding, and we encode the next layer, for which we put the accuracy to 0, because this is the layer that we want to predict. This goes in the TAP again and does another prediction. This iterative process ends when we encode the last 2 layers, and the accuracy, the final accuracy that the TAP predicts, is the accuracy of the entire network. We decided to take this approach instead of encoding everything and let the network learn how to propagate these accuracies, because we've seen that it steers the prediction in a better direction than doing the full encoding of the full network once. So skipping this iterative process. Any questions so far? I don't see the chat. Okay, I'll assume there are no questions. We compare our approach with two state-of-the-art accuracy predictors. One is the Peephole, which I already mentioned. This is only looking at the network structure and tries to do a prediction based on the network structure, while the LCE is a learning curve extrapolator. This one requires at least 20% of the network to be trained, the network for which you want to do the prediction. Therefore, it's a bit slower. So it looks at the first part of the learning curve and then tries to extrapolate it. We've tested our accuracy predictor in 3 scenarios. Scenario A, which is presents the results in the first column, in the first row, sorry, considers that we train our accuracy predictor and the Peephole on the CIFAR 10 dataset, and then we try to do predictions of networks also on the CIFAR 10 dataset. We did this, although we know that this is not the main reason why we designed the accuracy predictor. So like I said before, we want this accuracy predictor to work across datasets. But it's an important use case to test against state-of-the-art algorithms like the Peephole and LCE. We've compared our results with 3 different statistics: the MSE, which is the mean squared error. It's the error between the predicted accuracy, which is on the y-axis, and the accuracy obtained through training, which is the x-axis. And this MSE should be as small as possible, because the difference between the predicted accuracy and the trained accuracy should tend to 0. The other 2 metrics, tau and r-squared, measure how well is the ranking done between the predicted accuracy and the training accuracy. The higher the number, well, the maximum is 1, but the higher the number, the better the predictor. We see that in this scenario, our accuracy predictor has the best performances compared to the Peephole and LCE. And even without the numbers from the plot, we see that it's mostly aligned with the ideal line. The second scenario, we've employed, I forgot to say that we've employed in this experiment 11 datasets. So our long life database of experiments contains roughly 800 experiments for each dataset. And in this scenario B, we train our accuracy predictor on all the experiments that we have, regardless of the dataset, and perform a 10-fold cross-validation. This means that the accuracy predictor sees 90% of all our experiments and tries to predict the 10% left. And because if you only do this once, you might be lucky by the splitting and have good performances, we repeat this 10 times and shuffle the data around in such a way that you would always, at the end, you will predict every network at least once, actually exactly once. So we perform this k-fold, 10-fold cross-validation. And again, we compare with the Peephole and the learning curve extrapolator. And the Peephole, because like we said, it was dataset specific, and here we employed 11 datasets, the prediction is not really reliable. We see this by the big scattering in the dots. The LCE is much better than the Peephole, but it's much slower, because for each point that we see in the plot, the LCE already saw 20% of the learning curve, which means that we've already trained for 20% of the time, which means, well, it's more expensive than just doing a prediction without training at all, but it has better performances than the Peephole. Our predictor is better than both of them and as cheap as the Peephole because we don't require any training before. We just look at the network structure and the dataset number. Although these two cases show a very good prediction of our accuracy predictor, it doesn't show the ultimate target that we had in mind. The ultimate target is a real case when a user comes with a completely unseen data set, and we want to make predictions for that data set as fast as possible. In the Peephole case, what they would do with a completely unseen data set, they would have to train the accuracy predictor, and to train their accuracy predictor means they would have to have ground truth for that. Having ground truth for that means they would have to generate 800 networks, that's what they do in the paper, train all the 800 networks, and then being able to train the predictor, and then they would be able to make a first prediction. What we want to do is to avoid this ground truth gathering, which requires a lot of training, but we want to employ all the experiments that we've already had, maybe on similar data sets, and learn from those. This is scenario C, in which, like I said, we have 11 data sets, and we perform an 11 leave one out cross-validations. This means that at each step, we train on 10 data sets, and we aim to make the AP make good predictions on the 11th data set. In the left-hand side, we see how this accuracy predictor would perform without the dataset characterization number. If we remove the dataset characterization number, or we just put it 0 all the time, then this accuracy predictor just becomes like Peephole, completely dataset unaware. So the predictions are going to be very scattered and very bad. In the middle plot, we use the dataset characterization number, but we do not perform the lifelong database filtering. So when we want to predict for the 11th dataset, we actually train on all the 10 left datasets. This is giving better performances than without the DCN, but the results are still not as good as expected. So we went one step further, and we trained the accuracy predictor only on datasets that are close in difficulty with the dataset that we want to target. So the 11 leave one out cross-validations would be 11 trainings, but only on datasets that are close in difficulty. And this gives much better performances. And if we actually check with the state of the art, in this case, we cannot actually compare with state of the art because they are all dataset specific. But if we only look at the metric, at what values our metric have, then these values are quite similar to the Peephole and the LCE when they are trained in a very favorable cases like scenario A and scenario B. Therefore, we can say that this accuracy predictor actually makes very good predictions without even seeing the dataset before, with only one constraint. In our lifelong database of experiments, we have to have datasets that are close in difficulty. Otherwise, we fall in the case of the Peephole, and we have to actually generate networks and gather ground truth that it's close to the dataset at hand. We use this accuracy predictor in a large-scale evolution. So we replicated their results, the Google's results, but instead of training all the mutations that we generate, we just predict them with the accuracy predictor. Therefore, our timings are much smaller. So instead of 10 days on 250 GPUs, we generated this plot in 400 seconds without needing a GPU. But at the end, what we have is only predictions. So we have to make sure that our predictions are quite correlated to the real value. Therefore, we just took the top 3 and we actually trained them. And we see that the predicted and the trained values are quite similar, and the rankings are also very good. Now, there is 1% difference from the state of the art. And there is one thing that I didn't mention after doing this training. We also employ some learning rate schedules because we've seen, and from our experience, this is very important in getting the last few percentages. Conclusions and future work. Well, we presented an accuracy predictor that is dataset agnostic, that leverages experience from previously trained networks that before would just been trashed, and that's a lot of resources that have been used in those experiments, and they are practically useless if we don't employ them further on. We presented a real-time prediction that scales with the resources, and we employ our accuracy predictor in an architecture search, and we've seen that it goes to the expected performances. We plan on extending this work for object detection. This would be the most natural extension from image classification. Probably also to video, text, but that's future work. We are currently embedding this into an IBM cloud product. And we also deliver this on Open Power. Thank you for your attention. Any questions? Then I was quite clear.
Yeah, no, that was very clear. Hi, this is Jim Spoor. Could you say more, and maybe go back to the slide on explaining a little bit more about what accuracy means?
Yes, of course. Okay, let's see. This slide is okay?
Yeah, that'd be great.
Okay, so let's say we have a data set containing 10 classes. Images of cats, dogs, I don't know, ship, cars, etc. We want, when showing a picture to a network, we want that the network would know that in that picture is a cat. If the network correctly identifies a cat in the picture, then we say that, let's say, one example was correct, and if we, let's say, do this 100 times, and 98 of the cases, the network actually correctly identifies what object is in the picture, then we have a 98% accuracy. So is how many times the network correctly identified the correct class in the picture.
Correct class of the picture. Got it. Thank you. Just wanted to make sure.
Yeah, no problem.
It's like magic. the whole approach. Any questions for Roxana? Other than the open source one, there is an open source question.
Yeah, please go.
Yeah, so this is Jim again. Sorry to dominate the questions here, but I was wondering if that probe nets, is the data that's trained up on open, and is the model open? I'm wondering if it could be part of the model asset exchange.
Well, the model is, what do you mean by open? Like you have access to it and you can run it yourself?
Yeah, downloadable from GitHub under a license.
Well, downloadable, no, but the full structure is defined in our paper, which is very easy implementable if you want.
Yeah, the code is, but is the data that you trained it up on, is that available or not?
Yeah, all the data sets that we have are available. 1 second, let me minimize everything here.
Okay.
And are these data sets that I've shown here. So all data sets are publicly available, NIST, CIFAR 10, Flowers. Indeed, I'm not sure if there is a place where you can gather all of them at once. Mm-hmm. They come in different flavors, in different formats, and we actually had to put a lot of work in.
Yeah, I bet. Okay, cool. Thank you very much, Roxana.
Okay.
Any other questions?
I see that one question in the chat. How is ProbNets created? is the data that goes into ProbNet open and available? I'm sorry. You already
Yeah,
asked.
you've answered it. Yes. Yeah. Any other questions or thoughts, or if you enjoyed the talk, please thank Roxana in the chat for her great and concise presentation. Okay, it looks like people enjoyed the session.
Okay, I'm glad.
Yes.
And well, for further questions, I'm just gonna add my email to.
Yes. Oh, yes. Yeah. Why don't you do that? And also, I think you have it. The slides already uploaded, and the presentation, the recording will be uploaded soon. And maybe we'll talk to you separately about what could be made available for others to use in open source, but that will be a separate discussion. Yeah. Yep. You've got some great feedback, Roxana.
Yeah. Thank you very much.
Yeah. Yeah. Oh, yeah. So somebody says they want to get back in touch with you, which is good. And you put your email so they can do so. Okay.
Yeah.
Well.
Okay. Thank you very much.
Thank you. Thank you, everyone. And we'll meet again next week. Thank you, Roxana. Bye-bye, everyone.
Bye-bye.
Thank you. Bye-bye.